Good morning, this is Dr. R.K.Arya. Today I am going to explain conduction in a two-layer medium. So in this case your problem statement is, this is your problem statement. Let a long resistance wire of radius R1 equal to 0.2 cm, thermal conductivity K wire equal to 15 watt per meter per degree Celsius, in which heat is generated uniformly as a result of resistance heating at a constant rate of E dot generation 50 watt per centimeter cube. The wire is embedded in a 0.5 centimeter thick layer of ceramic whose thermal conductivity K ceramic is 1.2 watt per meter per degree Celsius. If outer surface temperature of ceramic layer is measured to be Ts equal to 45 degrees Celsius, determine temperatures at the center of resistance wire and the interface of the wire and the ceramic layer under steady state conditions. So these are the assumptions or conditions we have. Heat transfer is a steady state since there is no change with time. Heat transfer is one-dimensional since there is two-layer heat transfer problem, possesses symmetry about the center point and involves no change in axial direction, so T is purely a function of R. Thermal conductivities are constant. Heat generation is in the wire and is uniform. So this you will say that wire is this one of radius R1, and on top of that you have a ceramic layer just to give the insulations and is maintained at outside temperature Ts equal to 45 degree. This is the interface here, so here you have a temperature T1. Heat transfer is getting transferred from center of the wire to the ceramic. So in this case, if you say steady state heat transfer case, so in radial directions, so this would be the equations, and here this accumulation term is getting cancelled. So you have 1 upon R, d upon dr, R, T dr, d wire upon dr plus E dot generation equal to 0. This is under steady state within the wire. Now what boundary conditions we have for wire section is T wire at R1 means as you will move at this particular point, this will have a interface temperature Ti. At center, this is the center line thermal symmetry boundary condition, dTr upon dr equal to 0. This is thermal symmetry boundary conditions. Now we have this equation, so we can integrate that. So if you integrate that, you will get R dt wire upon dr equal to minus E dot generation upon K R square upon 2 plus C1 at R equal to 0, dtr upon dr equal to 0. So if you substitute here 0, so you can calculate your C1 equal to 0. Now you have dt wire upon dr equal to minus E dot generation R upon 2k wire. So T wire equal to minus E dot generation R square upon 4k wire plus C2. Now at R equal to R1, T wire equal to Ti. So you can substitute here. So you will get expression of C2 in terms of interface temperature. Now substituting that, you have T wire equal to Ti plus E dot generation upon 4k wire bracket R1 square minus R. Now for ceramic layers, no generation of the energy within ceramic layers, so E dot generation is 0. So for that, under steady state, this equation need to be solved. So d upon dr r dt r dt ceramic upon dr equal to 0. So now this can be integrated. So dt ceramic upon dr equal to c3 upon r. So for integration, there t ceramic equal to c3 ln r plus c4. Now boundary conditions are at R equal to R1, T ceramic equal to Ti, because that is the inlet temperature for ceramic, which is equal to the interface temperatures as T wire and T ceramic. At R equal to R2, T ceramic is equal to Ts surface temperature of ceramic layer. So by putting these two conditions there, so Ti equal to C3 ln R1 plus C4 and Ts equal to C3 ln R2 plus T4. We can solve these two. So from here we will get C3 equation 2 minus 3. C3 is Ti minus Ts upon ln R1 upon R2. Now from equation 2 we can calculate your expression for C4 Ti minus Ts ln R1 upon ln R1 upon R2. Now T ceramic expression is finally Ti plus Ti minus Ts upon ln R1 upon R2 ln R upon R1. Now we have one more condition, the heat flux boundary condition. So whatever heat flux in wire at interface would be equal to heat flux in ceramic at the interface. So by putting this condition here, that minus k wire dt wire upon dr at R equal to R1 equal to minus k ceramic dt ceramic upon dr at R1. So by equating that, you are getting this minus k wire minus E dot generation upon 2 k wire into R1 equal to minus k ceramic C1 upon R1 equal to minus k ceramic upon R1 Ti minus Ts ln R1 minus R2. So by solving this, we are getting expression for Ti. So interface temperature E dot generation R1 square upon 2 K ceramic ln R2 upon R1 plus Ts. So here every parameter is known to us, so we can calculate what is the interface temperature. Once we know now expression of interface temperature, so we can calculate T wire. So T wire is Ts E dot generation R1 square K ceramic ln R2 upon R1 plus E dot generation 4K wire T R1 square minus R square. So by changing R, we can calculate the wire temperature. So at the center, I just put R equal to 0, substituting all these parameters from here. We got the temperature here equal to 152.7. T interface temperature can be calculated from here by substituting the values. So T interface is 149.4. And reference for this, this is being taken from Heat and Mass Transfer Fundamentals and Application by Sengel. Then another book by Sengel is that Heat and Mass Transfer, a Practical Approach. So thank you very much. In case of doubt and comments, you can drop. Thank you very much.